deadly facts about water. Water is the leading cause of drowning, in case you didn't know. Water is one of the primary ingredients in herbicides and pesticides. 100% of all people exposed to water will die. 100% of all serial killers, rapists, and drug dealers have admitted to drinking water. Overconsumption can cause excessive sweating, urination, and even death. Yeah, so there you go. Some fun. Okay. Because we're talking about water. It was like a funny joke. It is facts, though. They are facts. They are true. They are not false. Okay, so most liquids in solid state, we're going to be talking about a lot of different things today and just spitting a lot of things out there, okay? So typically solids will sink in their own liquid, except for water. As the liquid cools, it begins to contract and the density increases gradually, so that's why because it's more dense, it will sink to the bottom, because the molecules move closer together. So did everybody write down sink? Yeah? Okay. This takes forever. I should change that. The water in the solid state, ice cubes, on the other hand, if you would throw some ice into water, the ice cubes float on the surface, which is not usual for other substances. Because initially water will behave like a typical liquid as it cools, and it will slightly contract, and density will increase until it completely freezes. But this picture up in the corner, which I know it may be hard to see, is showing how there is actually spaces in between the water molecules when it freezes. And so because there's those spaces, there's air pockets. So that's why it makes it actually less dense. So solid ice has a lower density than liquid water. The structure of ice leaves space for air because of its hexagonal structure. So normally, like, we think of ice cubes, right? Well, you can think about an iceberg because, normally most of an iceberg is not seen on the surface because it's floating in the water. The longest part of this whole video are those transitions. So solutions. Next chapter is all about solutions, and we have to do some equations with solutions. But water dissolves many substances that it comes into contact with. When it dissolves, an aqueous solution contains water-dissolved substances. Okay? In a solution, the dissolving medium is called the solvent, and the dissolved particles are called the solute. So water would be the solvent because it's what's doing the dissolving, and the solute is whatever you're putting into the water. Okay? Substances that dissolve most readily in water include ionic compounds and polar covalent compounds. We should already know that. When we dissolve stuff, we have what's called the solution process. Water molecules are continuously in motion because they have kinetic energy. So when a solid crystal is placed in the water molecules collide until it breaks down the crystal. When it does that, for example, in this picture, I have sodium chloride. So then the water molecules will surround the ions so they can't bond back together after they've been broken up. And so this process of surrounding with solvent molecules is called solvation. And so this is another example of ionic salt, NaCl, dissolving. And so if you look, the oxygen are the reds, and so that's surrounding around the sodium, which has a positive charge. And then around the negative chlorides, the hydrogens are going to it. Good things to know. Opposite charge attract. In some ionic compounds, the attractions among the ions in the crystal are stronger than the attractions by the water. So therefore, these compounds can't be solvated or can't be dissolved. So we call those insoluble. Back in chapter 11, when we did states of matter, we would just have that thing in our solubility rules list that said insoluble. So two examples of insoluble compounds are calcium carbonate and barium sulfate. If you want to be super cool, you can write those chemical formulas out instead of their names. So from nonpolar molecules, these don't dissolve in water because like dissolves like, and nonpolar, water's polar, they can't do the same thing. They use different solvents instead. So some other examples for nonpolar molecules would be like gasoline or turpentine or acetone. Like nail polish, you can't just get it off with water, right? You have to use a special nail polish remover, which usually includes acetone. Or like if you get oil-based paint on your hands, it's not going to come off unless you use like gasoline or some like paint thinner to get it off of your hands for you. And that's because they're non-polar, so water is not going to do anything for it. Okay? Just write a couple of those down. You don't have to write them all. Alright, when we do have solutions, we have things that are called electrolytes. An electrolyte is a compound that conducts an electric current when it's in aqueous state or in the molten state. A non-electrolyte means it doesn't conduct an electric current. We hear about electrolytes a lot of times in Gatorade. In our project for this chapter, a lot of people like to use Gatorade as an example. You can too. But they advertise that you need to replenish your electrolytes, right? So electrolytes are the reason that we don't use hair dryers or toasters in the bathtub, which please don't be eating toast in the bathtub. That's kind of weird. But the whole reason is because when you dissolve something in water and it produces electrolytes, that causes an electric current to be passed through the water. And so even though we think of tap water as being safe, it does have stuff dissolved in it. And so technically, theoretically, it could conduct the electric current. If you filled a bathtub with distilled water, theoretically, it should be okay, but let's not test it. Just to be safe. Let's just not. Okay? So strong versus weak. Not all electrolytes are the same way. Okay? A strong electrolyte is where nearly all of the solute exists as ions, and so then it conducts electricity very well. Versus a weak electrolyte, which conducts an electric current poorly, because only some of it will break apart into its ions. We'll get more into that, and acids and bases have two different bases in chapter 18. So electrolytes are essential to all metabolic processes. That's a big word, so I don't teach biology. Cells in the body use electrolytes such as sodium and potassium to carry electrical impulses internally to others. So it helps with your neurons and the transferring of electric current in your body to make sure things move. So there you go. We're almost finished. We're talking about hydrates now. We were using a hydrate with our growing up crystals. The copper sulfate we used was a hydrate. Water molecules are an integral part of crystals in a lot of ionic compounds. So when water is contained in a crystal, we call it a water of hydration or the water of crystallization. Usually, the water in a crystal will actually give it a bright color. So in this picture, there is a hydrate versus an anhydrous form of the same compound. Okay? So a compound that contains water is called a hydrate. An example of a hydrate was our copper 2 sulfate pentahydrate, which we used for our crystal growing, and it was a very nice deep blue color. You can still look over there and see some. But it's because it actually has 5 water molecules within the structure. You could write down that cool formula instead of, writing the whole name down if you want. The forces holding the water molecules in hydrates are not very strong, so the water is easily lost and regained. Woo. Some common hydrates that we have around our houses, maybe. Epsom salt is actually magnesium sulfate heptahydrate, so it has 7 water molecules in the structure. Borax is sodium tetraborate decahydrate. We used borax when we made our green slime at Halloween. Do you remember that? And then calcium chloride dihydrate is just another one. That's actually used as a desiccant. And we'll talk about that more tomorrow. So any substance that doesn't have water contained in it is called anhydrous. So anhydrous, if you would add water to it, it would turn that colorful blue that we've seen in our copper sulfate. The anhydrous solid doesn't have any vivid color though, it's like a chalky kind of color. We also have efflorescent hydrates. It's one of my favorite words to say. The water vapor molecules in hydrates are held by weak forces, so hydrates often have an appreciable vapor pressure, meaning they actually matter. If a hydrate has a vapor pressure higher than the air, or the pressure of the water vapor in the air, then the hydrate will lose its water of hydration, or what's called effloresce. So it's losing water when it does that. it'll just kind of dry itself out. On the other hand, we have hygroscopic hydrates. Hygroscopic hydrates are ones that actually remove moisture from the air. So for example, calcium chloride monohydrate spontaneously absorbs other molecules when it's exposed to moist air. So these things are what are found in like silica gel packets when you buy like shoes or bags or whatever, you know, like you see those little packets. Those are called hygroscopic hydrates inside those packets. You're not supposed to eat them because that can make you sick, but they're absorbing moisture so they keep the product of whatever you bought nice, you know, and still good. So another hygroscopic thing that we use in here a lot is sodium hydroxide. That's one of those things. It's the one where if you get it on your skin, it'll start to itch and chemical burn yourself, right? And I like yell at you if you keep the lid off, because if you just let it sit open, instead of being like nice little pellets, it will turn into a big solid block. And then we can't use it anymore because people are going to have to chip away, and then they're going to get on their skin, and then that's bad. So we use hygroscopic things a lot, but that's just one reason why we like to keep bottles covered. So that's it.